So thanks a lot for having me. It's a pleasure. Um, so today I will be telling you about a series of works that was done in collaboration with these fantastic collaborators, Yuji Tachikawa, Kazuya Yonekura, and Kantaro Omori. And the topic is non-supersymmetric heterotic branes. Okay, so let's jump right into it. So we're all familiar with the E8 cross E8 and SO32 heterotic strings. It will be very important later on that the actual global form of the gauge group of these theories is not just E8 cross E8 and SO32, but rather this Z2 semi-direct product E8 cross E8 and this Z2 quotient of spin 32, which is not SO32. Okay, but we'll come back to that later. In any case, we're very familiar with these theories. Something which is somewhat less familiar, um, at least to most audiences. For this audience, it might be equally familiar, but for most other audiences, it's somewhat less familiar that there are actually other string theories in 10 dimensions, which include a theory with E8 gauge algebra, a theory with U16 gauge algebra, so on and so forth until O16 cross O16 here. Okay. In fact, until fairly recently, it was unclear if this was even the full list. For all we had known, there could have existed some exotic C is equal to 16 spin CFT that could have given us a new 10D heterotic string. But thanks to recent classification efforts, it's now known that this list is complete. Okay. But so why are these theories less familiar to most people? The reason is that they're non-supersymmetric. And of course, being non-supersymmetric itself is not a bad thing. It's sort of a good thing. But the problem is that when you don't have supersymmetry, for the most part, you also end up having a closed string tachyon. For this O16 cross O16 case, there's actually no tachyon, but this has a massless dilaton tadpole, so it has its own issues. So for that reason, people usually don't, well, focus as much on these guys as the other guys. Okay. But of course, as we all know, having a tachyon might be worrying, but it itself is not really fatal. It just means that you're expanding around the wrong vacuum. So, for example, if your theory looks like this, you have some potential here, then of course this will be some vacuum, but it'll obviously be unstable. And so you'll want to, you'll have a tachyonic mode, but you might be able to condense the tachyon. And if there exists some minimum here, and I'll only be interested in perturbative stability in this talk, um, so this just has to be a local minimum. So as long as there exists some local minimum, then you can condense the tachyon and then roll down, and everything is okay. And indeed, for these string theories, the non-supersymmetric heterotic strings with closed string tachyons, you can do this tachyon condensation. Okay, so you start up here in 10D Minkowski space. That's where you have the tachyon. And it turns out that you can condense this tachyon and you can get some lower dimensional vacuum without a tachyon, so it's perturbatively stable. The funny thing is, though, that this is not a Minkowski vacuum anymore. It's going to have some linear dilaton. Okay. And in previous iterations of this talk, I actually went through the tachyon condensation procedure, which was basically the topic of this solo single author paper I had out at some point, which was just an extension of some previous work by Hellerman and Swanson. But in today's talk, I want to discuss more, well, other things. So I'm not going to focus so much on this tachyon condensation. I'm just going to quote the results. So it turns out that if you start, for example, in this E8 heterotic string, you can condense the tachyon, and what you'll get out is you'll get out a vacuum which is in 9 dimensions, okay, but it's not Minkowski space. Okay, so you only have 8-dimensional uh, Lorentz symmetry, and then you have this extra direction here, which is actually a linear dilaton. Okay, but so it's some 9-dimensional vacuum, and the gauge group, or really algebra, is again E8. And in the U16 case, you can again condense the tachyon, and now you'll get out an 8-dimensional vacuum here, again with some linear dilaton, and the gauge algebra becomes SU16. For this E7 times SU2 squared case, you get a 60 vacuum, okay, with E7 squared gauge algebra. And for the remaining cases, you get 2-dimensional, a stable vacuum. Okay. So the upshot here is that it turns out that you can condense the tachyon and get stable lower dimensional vacua in dimensions 9, 8, 6, and 2. Okay. An interesting thing about the 2D vacuum, the 2D vacua, is that so back in the maybe early 2000s, people were really interested in 2D strings, and there's some papers that classified 2D heterotic strings. And what they found is that there's three of them. And in fact, this is exactly those three. Okay. Anyway, so you get these stable lower dimensional vacua, but they all have a linear dilaton. So one question is, how should we interpret these
Sorry, just
vacua?
Justin,
Oh,
just a
yes.
quick question. For the 2D heterotic strings on the other side, what was the difference between the two
Oh,
2D
this one and
theories,
this
the
one.
same gauge group? Yeah, yeah.
Yeah, they're
What's are they
related by a
different
Z2
massive
gauging.
spectra? Okay, sure. Is their massless spectrum the same or
Uh, y yes, I think so. I don't really remember, to be honest.
okay,
I
okay,
just remember that they're related to some Z2 gauging.
okay, sure. Yeah.
Sorry.
Yeah, no, it's fine.
Any other questions? Okay, good. Good. So how do we interpret these vacua? So we're going to take as a hint the fact that there's a linear dilaton. Okay. So uh, remember that another place in string theory where a linear dilaton arises is in the near horizon region of an NS5 frame. Okay. And so we might guess, this is just a complete guess at this stage, but we might guess that these non-SUSY strings exist in order to describe the near horizon regions of some new branes. Okay. And what can we say about those branes? Well, just based on counting alone, so we had 9, 8, 6, and two-dimensional vacua, and those would be appropriate to describe near horizon regions of 7, 6, 4, and 0 branes. There's always a shift of 2 because if you have, for example, a 0 brane, the actual world volume of it is one-dimensional, and then you have the linear dilaton direction. Okay. Okay, so one might guess that you would have a 7, 6, 4, and 0 brane. These would be branes in the familiar supersymmetric heterotic strings, but they'd be branes that break all the SUSYs because those vacua I had given you before were non-supersymmetric. Okay, and of course, no such branes are known, so at this point, this is just some baseless guess. But on the other hand, we can turn to a separate question, which is, so we all know that there's this old quantum gravity lore that states that any consistent theory of quantum gravity should have objects that carry all possible charges. This is basically the only swampland-esque slide I'll have in this talk, but this is very important. We're all familiar with this. Okay. Um, and so what I'm going to be talking about are a set of sort of magnetic charges for these gauge groups E8 cross E8, semi-direct product Z2, and spin 32 mod Z2. Okay. So note that these gauge groups have these non-zero homotopy groups. This is almost all of the non-trivial homotopy groups. There's one other I haven't written down here, which is pi 3 of spin 32 mod C2. I'm not going to talk about that, but you can ask me about its implications later. But in any case, we have these non-trivial homotopy groups. And as we all know, what homotopy groups tell us is they tell us about some sort of non-trivial gauge configurations on spheres. So in particular, if you have an n sphere, then in order to get a non-trivial gauge configuration on the n sphere, you split it up into northern and southern hemispheres, and then you glue them along the equatorial Sn minus 1 with a non-trivial map from Sn minus 1 to G. So in other words, some element of pi, some non-trivial element of pi n minus 1 G, right? So in particular, this pi 1 here of spin 32 mod Z2 is telling me that there's some non-trivial gauge configuration on S2 that I can build. Okay. And if we take the quantum gravity lore seriously, we would expect that there exists an object which can source this gauge configuration and that can live in the center of this S2 and source this gauge configuration. So in 10D, the object that can sit in the center of an S2 is a 6 brane. Okay. So this would predict that there's a 6 brane in the spin 32 mod Z2 heterotic string. And similarly, this would tell me that there's a 7 brane. This would be appropriate for having a 4 brane, and this would be appropriate for a 0 brane. Okay, so in other words, in order to capture these non-trivial configurations on S1, S2, S4, and S8, we would expect that we would have some 7, 6, 4, and 0 branes. Okay, and note that this sequence of numbers 7, 6, 4, and 0 is exactly the same as before. Okay, so maybe these two questions are related. Maybe there exists some new branes that source these non-trivial gauge configurations and whose near horizon limits are those lower dimensional vacui I had identified before. Okay, and so today what I want to argue is that indeed that's the case. Okay, so that's the idea. So now I'm going to explain this connection in detail. Are there any questions? Okay, good. So then, in order to prep ourselves for the following discussion, let's first review the NS5 brane. Okay, so remember that the starting point for an NS5 brane, so our starting point for this talk will just be some supergravity solution. Okay, so you can write down the following extremal solution for an NS5 brane. So you have the metric here, you have the parallel directions to the NS5 brane, the perpendicular directions, which you can, of course, write in polar coordinates. This is r squared d omega 3 squared. Okay, this is the unit metric for the 3 sphere. Okay, you have this dilaton profile here, and you have some H field, and also we're in the heterotic string, so there's also some gauge field. Right? Okay, now I'm going to take the near horizon limit. When I take this, so the near horizon limit is, of course, this r goes to 0 limit. When I take this limit, the dilaton just looks like this. And if I plug this into the metric, then I just get this. And now let's just do a coordinate transformation to set y equal to log r. Then the metric looks as shown here. The dilaton is as shown here. So what does this look like? It basically looks as follows. So when you're really far away from the brane, of course, you just have flat space. But then, this is a bad drawing. Okay, you have flat space. But then as you approach the brane, you go to the near horizon limit, and you see that what you have is you have this infinite throat, which is parameterized by this y coordinate. Okay, and the dilaton is linear in y. And at every point in this throat, you have a constant radius S3. Now, I haven't written down H here, but it's important that you have a unit H flux through this S3. That's what sort of supports the S3. Of course, you could consider more than just one unit of H flux. You could consider multiple units of H flux through this S3, but that would correspond to multiple NS5 branes. So if you want the minimal NS5 configuration, you choose the minimal charge, the minimal flux. Okay. Okay, so the extremal near horizon solution for the NS5 brane, as we all know, is as shown here. Okay, so you have this throat with a linear dilaton and a unit H flux through the S3. But there's actually a problem with this. It turns out that this supergravity solution is not reliable in the alpha prime sense, because this S3, when you have only a unit of H flux, one unit of H flux, this S3 has a very, very small size. Okay, so this R0 in that case goes something like square root of alpha prime. So the supergravity solution is not actually reliable. And so one thing that you can do is transfer to a worldsheet description. And so in particular, there's an exact worldsheet description for this near horizon solution that was given by these people here. And what does it look like? Well, you take this parallel part that just becomes this R15 here. And more precisely, what R15 here represents is it represents the 0, 1 linear sigma model, R15, on R15, right? And this linear dilaton, R linear dilaton here, of course, refers to a 0, 1 linear dilaton CFT. Everything is 0, 1 because we're in heterotic string, right? And then this S3 becomes an SU2 WZW model, okay, at some level. The level is basically just determined by how many units of H flux you have. So when you have one unit of H flux, it's, I don't remember exactly, but maybe -2 or something like that. And then you have the current algebra, right? You're in the heterotic string. Okay, so this is the sort of worldsheet translation of this. So this turns out to be the exact worldsheet description. Of course, when we say exact, there's some caveats here, um, because well, when you go very close to the NS5 brane, you have to so the string coupling blows up. And so actually there's sort of a different sense in which things become unreliable because then you would have to do it. I mean, perturbative string theory is probably not even a good way to describe that really, really close to the NS5 brane region. So when we say exact worldsheet description, what we sort of mean is we're in an intermediate regime where you're close enough that you're actually in the near horizon limit, but you're far away that you can pretend like you're at weak coupling. But anyways, uh, let's forget about that. So, right. So the intuition here, so one intuitive way to think about this is you can think of the near horizon regime, this worldsheet piece, as saying that you have a 70 vacuum, which is this part, and then you have this SU2 times G gauge group. And then these authors here, the way they interpret this is basically as saying that the 70 vacuum is like the holographic dual to the 60 little string theory that lives on the NS5 brane. Okay, so some picture like this. This is where the little string theory lives. This is the 70 vacuum that I just mentioned above. Okay, this interpretation is really not going to be important at all for what I'm going to say, but in any case, this is one way to think about things. Okay, so that was sort of the lightning review of the NS5 brane. And if that's okay with everybody, I now want to generalize this to the six brane case. And then after introducing the six brane, I'll introduce the other branes as well. Any questions about the NS5? Okay, then I'm going to move on to the six brane. So we're going to do a similar thing for the six brane. Remember that our goal, let me go back to the beginning. So the claim was that, so this guy would be a six brane. Okay, this is, remember, the 8D vacuum with SU16 gauge group. And I want to interpret this as the near horizon limit of some six brane. Okay, so that's what I'm going to aim to do right now. Uh, okay, so that's what I wrote here. So I don't, so I'll tell you what the level is in a second. But at this stage, this is what I'm aiming for. Okay. And what's my starting point going to be? My starting point is going to be the same as for the NS5 brane. Namely, I'm going to write down some supergravity solution for you. In fact, a supergravity solution describing a black six brane in the SO32 heterotic string was already known since the 90s. Okay. In fact, they wrote down this nice finite temperature solution. For our purposes, we only care about the extremal limit. So I'm going to take the extremal limit. I'll also take the near horizon limit. And this is what that previous solution from the 90s looks like. Okay. So it looks a lot like the NS5, right? So as before, you have this infinite throat here. But now, instead of having a constant radius S3 at every point in the throat, you have a constant radius S2, right? That's what surrounds the sixth brane. Okay? You have this linear dilaton here. And instead of having a unit of H flux that supports the S3, now you have some gauge flux that supports the S2. And there are these charges that appear in this flux, okay? Just like how you had supergravity solutions for any units of H flux through the sphere. Here you also have supergravity solutions for any charges here. But of course, you would like to choose the minimal value of the charges in order to get the sort of minimal six brane. Now, what's the minimal value of the charges? This is the sort of new thing that they didn't do in the 90s. So it turns out that for the gauge group spin 32 mod Z2, it's actually possible to choose these charges to be 1/2. Um, or half integer, I should say. For the if it was SO32, if the actual gauge group was SO32, by Dirac quantization, these things would be required to be integer. But for spin 32 mod Z2, they can be half integer. So the minimal value is to take them to be 1/2. And in fact, if you take one of them to be half integer, they all have to be half integer. Okay, so the minimal thing that we can do is we can just take all of them to be 1/2. So that's what we're going to do. We're going to take them all to be 1/2. One nice thing about having them all be the same, by the way, is that this preserves a U16 in SO32, this flux would. And of course, we want to aim, well, we expect this SU16 to pop out eventually. But, okay, anyways. So the minimal thing we can do is we can take all of these things to be 1/2. So that's what we do. Um, But unfortunately, we run into a problem which is the same problem as for the NS5, which is namely that when we take these charges to be the minimal value, this R0 is of course very small, it's string size. Okay. And so the supergravity solution is not really reliable. We should pass to a worldsheet description. And so now I'm going to tell you what the worldsheet description is. This is a bit more involved than for the NS5 case. But our starting step is going to be just to translate this supergravity solution into the naive worldsheet language. Okay, so I'm just going to translate it line by line, basically. So first of all, I'm just going to ignore the flux here. Okay, I'll add the flux in a second, but ignore this for a second. Then what this looks like is the following. I have the parallel directions. That's just a 0, 1 R16 linear sigma bond. Then I have this y direction and this linear dilaton. Okay, so this just gives me a linear dilaton CFT. It's again 0, 1. Then I have the S2. Okay, here's the S2. It's again 0, 1. But now I've explicitly written the 0, 1 for reasons that will become apparent in a moment. And then you have the current algebra. Okay, and if I'm forgetting about this flux here, then this is just some separate entity that is coming along for the ride. Okay. Okay, now what I'm going to do is I'm going to tell you that there's this nice identity which tells me that SO32 at level 1 current algebra theory is actually the same as SU16 at level 1 times SO2 at level 1 modded out by some Z2, which I've decided to write as -1 to the F left, but you don't have to think deeply about it. It's just some Z2 quotient. Okay, so this is just an identity. We prove it in an appendix. Okay. And now the very nice thing is the following. So now I'm going to reintroduce the flux. Okay. What does the flux do? Well, you can see, I mean, right, the flux is basically telling you that if I integrate this SO32, FSO32, okay, whatever, there's some number, then I get, some matrix here. Okay, so what it's doing, morally speaking, is connecting the S2 part with the SO32 part, right? The SO32 is non-trivially fibered over this S2. And when you make the choice that I made previously, where I chose all of the charges to be 1/2, then what happens is actually the following. It turns out that the vector bundle of this SO2 level 1 piece in SO32, okay, the vector bundle of this thing gets identified with the tangent bundle of the S2, this S2 here. Okay, that's the effect of the fluxes. Okay, so when you turn on the flux, this is what happens. And this is rather nice because, so I can think of this SO2 current algebra as being made up of two Majorana biofermions. So let's call them lambda L1 and lambda L2. I'm thinking of the current algebra as being on the left side, which is why I put the subscript L. But now you see that when you have this identity, then you can basically think of these guys here as completing this 0, 1 S2 nonlinear sigma model to a 1, 1 S2 nonlinear sigma model. Okay. And so when you turn on the flux, you see that the actual worldsheet theory is this. Okay. So this here is the worldsheet translation of this supergravity solution. Okay. Now, remember, what we wanted to do is we wanted to see what is the actual fate of this supergravity solution in string theory. Here I've translated that supergravity solution to the worldsheet. But now you can see that this is not actually a stringy solution, like a solution to the stringy equations of motion, because this isn't a CFT. So you have an S2 nonlinear sigma model. There, S2 has curvature, so this thing is not a CFT. There's going to be an RG flow. And this is pretty nice that we have a 1, 1 nonlinear sigma model here. because we know what the RG flow of this thing is going to look like. Okay. So as Witten taught us, what's going to happen here is that you're going to flow to a bunch of gapped vacua, one for every element or one for every de Rham cohomology of S2. Okay. And so in this case, what you're going to flow to is you're actually just going to flow to two gapped vacua. And it turns out that these two gapped vacua are exchanged by this minus one to the F left that I'm quotienting by. Okay. So I translated the supergravity solution to this, but this thing actually will now RG flow, and it's going to RG flow. The endpoint of the RG flow is going to be this. Okay. Okay, so this is exactly the vacuum that we had identified previously via closed string tachyon condensation in the non-SUSY U16 heterotic string. Okay. How exactly you interpret this RG flow in space-time is, of course, a little bit subtle. It's, of course, tempting to think of this as some actual dynamical process whereby the S3, the stringy size S3, sort of shrinks away, or sorry, S2, I should say. Stringy size S2 shrinks away, and you're left with a lower dimensional vacuum. But what if you can really think of RG flows as like as time evolutions in space-time? That's something which is not entirely clear. But what is clear is that the actual stringy solution here is this vacuum. Okay. Okay. So, so far so good. So I've shown that there's potentially this sixth brane. I wrote down supergravity solutions, and then I showed that the actual sort of near horizon limit of this thing is really described by this thing that we had obtained from closed string tachyon condensation previously. Let me also make a touch. Let me connect to the issue of charges. So what charge does the brane carry? Well, as I told you, it sources this flux here with the 1/2. Okay. And as I said, this 1/2 is allowed only for spin 32 mod Z2, okay, not for SO32. So it's incompatible with the vector representation's Dirac quantization, but it is compatible with the adjoint in one of the spinor representations. Okay. So basically, this is a flux which is allowed for spin 32 mod Z2, but it's basically, it specifies some bundle of spin 32 mod Z2, which cannot be lifted to spin 32 itself. Okay. So in other words, it can't be thought of also as an SO32 bundle. Now, the obstruction to lifting this spin 32 mod Z2 to spin 32 is given by some generalized Stiefel-Whitney class W2, and you can think of this as the thing that that this is like the charge that the brane carries, right? And indeed, this is the thing that tells you if you're in this non-trivial element of this homotopy group here, right? This Z2 is just coming from this quotient Z2. Okay, so indeed, this thing carries the expected charge as well. Okay, so we've made contact with the two questions. All right, so that's the sixth brane. Now, are there questions about the sixth brane? If not, I'm going to explain the other branes.
Yeah, I guess I had a
Okay.
question. So, when we're
Um,
thinking about,
yes.
oh,
Oh, yes.
sorry, I think there might be a delay. Can you hear me?
I can hear you.
Okay.
Yeah.
Okay. So for the sixth brain, so I'm thinking about the duality to type one. So over there I have a K theory tells me that I have a stable seven brain, which intuitively is kind of like you could think of it as like a flux tube type of configuration where I have some W2 in the normal directions. Um, is I guess is there like a I don't know a conjectured picture for like I don't know the strong coupling limit of the sixth brane possibly fattening up, or is that totally unknown?
Um,
Or should there be a
I
sixth brane
don't
in
know
type
what
one?
the I don't so I do not know what the S dual of the sixth brane is, but it is not the seven brane in type one or related to the seven brane in type one. One thing that I had thought originally is that maybe it's the endpoint of the seven brane in type one. The D7 can break on the D9. And in
Sure.
fact, I think it can break on in two ways. And so then you can have two separate endpoints, and then you can imagine bringing them together. so that you get a 60 soliton. This is sort of described in some paper by Oren Bergman and Gilad Lifshitz, I think.
Hmm.
And so, anyways, I thought that that 60 soliton would be related to this in the SO32 heterotic string, but I believe it's not.
I see, I see.
So, yeah, long story short, I do not think that this is directly related to the D7 in any way.
Sure. Yeah, I
Uh,
mean, I asked because the gauge group, the global structure of the gauge groups are conjectured to be the same. And so, yeah.
right, right. I
Mhm.
agree. Yeah, so I would expect that there is some sort of, well, yeah, I think there's probably some six praying in type one as well, but I don't know what it is yet. I don't really understand much of it. It's actually quite confusing because, well, let's see what I should say. So you see, when you go to the throat, so you have this linear dilaton here, right?
Mhm.
So when you go deep into the throat and you actually approach the sixth brain, then this is becoming very strongly coupled. So actually, in that region, you would think that a type 1 description is actually particularly natural. So maybe this thing has some sort of natural description in type 1. But it doesn't really, because in the type 1 description, it turns out that you end up having some actual singularity,
Mhm.
which is weird. Also, the tension is really weird. So the tension of this guy goes like G string to the -2 in the heterotic string, which is something that we're sort of used to. It's like an NS brain, like a NS5
Mhm.
brain.
Yeah.
In the type 1 description, you can see that it actually goes like G string to the -3/2. So it's like something in between a D brain and an NS5 brain. So I
Yeah.
suspect
Yeah.
that actually the type 1 description of whatever this thing is even more complicated than its heterotic description.
Sure. I see.
Uh,
Uh,
so the
interesting.
answer is I don't know, sorry.
Interesting. Well, interesting thoughts. Thanks.
Oh, thanks. Okay, any other questions? Okay. I can't tell if I'm going too fast or too slow. I'm too sleepy to so tell me if either of those is the case and I can either speed up or slow down. Okay. So I'm now going to tell you a little bit about the other brains. So the key tool in our previous analysis was this identity here. And then I also made a choice of flux, which was very convenient. It ended up identifying the vector bundle of this thing with the tangent bundle of some sphere. So it turns out that there are actually more identities of this type. And here's three of them that we're going to use. For example, this one is probably familiar to anybody who's read the Big Yellow Book on CFT, because in the Big Yellow Book, they tell you that the Ising model can be thought of as some coset model of E8 level 1 times E8 level 1 modded by E8 level 2. And that's basically this identity here. Actually, if you want to make this identity completely correct, there's a little bit more effort you have to do. You have to include some SPT phase, some ARF theory here, etc. But let's forget about that. Okay, so anyways, we have these identities, and now I claim that we can use these identities to get exact worldsheet descriptions for the 0, uh, 0, 4, and 7 brains. Okay, in basically the same way as before. So for the 0 and 4 brains, you literally just do the same thing as before. Okay, and so let me just remind you what we did before. Okay, you start with this part here, this like space-time part. So this is the direction parallel to the brane and the linear dilaton. And then you have these angular directions. Okay, so the angular directions is some sphere, and then you have G1, which is this, it's some current algebra at level 1, right? It's whatever, it depends on which heterotic string you're looking at. Okay, and then what we do is just as before, we use one of the identities from before. In particular, if we're looking at a p brane, we want the identity that has an SO8 minus p factor. And then we introduce a flux, which identifies the vector bundle of this with the tangent bundle of this. And so then we can combine them into a 1, comma 1 nonlinear sigma model. And then we do the RG flow, and we just end up with this piece here. This HK is just whatever this other piece is. Okay, so as an example, let's consider the forebrain. Okay, for the forebrain, I want to look at whatever identity has an SO4 factor. Okay, so I go back to my identities here. It's this one here. Okay, so you see I start in the E8 cross E8 heterotic string. Okay, I have this SO4 factor, and the remaining thing, which I was calling HK, is E7 times E7. Okay, so for that forebrain, you're going to end up with a 60 vacuum, which has E7 cross E7 gauge algebra. That's precisely, again, what we had identified from tachyon condensation in the non-SUSY heterotic string of type E7 times SU2 squared. Okay. So the results match perfectly from those coming from closed string tachyon condensation. And so unlike the six brane case, where supergravity solutions were known and we could start from there, in the 0 and 4 brane cases, the supergravity solutions were not known previously. So the worldsheet description was what we originally used. But actually, since our paper, in this paper, um, they actually found the supergravity solutions for the 0 and the 4 brane. Okay, so that's all nice. Now for the 7 brane, things are a bit more subtle. And now that I'm looking at the time, I suspect that I'm doing things too slowly. So, um, so if you have questions, so let me just say the 7 brane is more subtle. And why is it more subtle? It's more subtle because you see this S8 minus P for P is equal to 7 is an S1. So it's actually flat. And so this isn't CFT. And so there's no RG flow naively. So in this 7 brane case, what you do is, long story short, you put some holonomy on the S1. And then if you do that correctly, you'll have some tachyons. And then if you condense the tachyons, you'll find that you basically get the same thing as before. Okay. So the 7 brane case is a little bit more subtle. If you want to ask about it, please ask me. Um, and I can explain it, but okay. Anyways, I'll skip it for now. So let me summarize the physics part of the talk. So I've identified for you 4 branes. There's a 0 brane in the spin 32 mod Z2 heterotic string. Okay. I didn't explain this actually, but it turns out that this brane is an endpoint for the heterotic string. It's actually necessarily attached to a fundamental string in the heterotic string theory. This is the 0 brane here. So in fact, that heterotic strings could end was already pointed out in this very prescient paper by Polchinski. Okay, so he had already basically identified the 0 brane. Now, we also identified a 4 brane in the E8 cross E8 heterotic string. One nice thing about this brane is that it has an interpretation in Hajava-Witten theory. So if these are the M9 planes, okay, if you take an M5 and you just stretch it like this, okay, so that its endpoint sort of gives some instanton in these M9s, uh, and then you take the heterotic limit, then this thing becomes our 4 brane. And actually, this configuration of an M5 ending on the M9s was also studied in some previous paper. Again, a prescient paper. So they also basically understood the 4 brane. The 6 brane, I think, is probably really, there's no previous literature that suggested it. So this is the one that I focused on mainly, and we saw that it sources a gauge configuration without vector structure. Some spin 32 mod Z2 bundle, which is not an SO32 bundle. And finally, the 7 brane is in the E8 cross E8 heterotic string. I didn't really explain it that much, but its nice property is that if you take so it has monodromy for the permutation Z2. So basically, if you go around the brane, your 2 factors of E8 get swapped. Okay, so that's sort of the SparkNotes version of our physics results. Okay. So are there any questions about that? So I want to make some math comments too. But are there any questions about what I explained so far?
So yeah, I would have a question.
Okay, please, yeah.
Hi. So in the last one, the 7 brane, you can also interpret the brane as sort of an endpoint, also of M theory, I guess, on a Möbius strip. Can you gain something out of there in understanding whether there are M theory objects ending on this or similar things?
Let me think. So, right. So the thing that you're saying about M theory on the Mobius strip is, yeah, this sort of CHL type thing. So sorry, was there a direct relationship between that and the 7 brane?
Yeah, so I would say the 7 brane is sort of like a Bordism of M theory on the Möbius strip, right? Because This is where you go around a circle, which is the circle of the Möbius strip, and you flip the 2e8 factors. So in the heterotic, it's exactly the configuration that you pointed out. And now you just ask the question is like in
Oh,
M
oh, sorry.
theory, how can I fill this object in and can I gain
Yeah, yeah,
some?
yeah, yeah. Yeah, sorry, I see. So yeah, you're asking, yeah, so there should be some object in M theory which makes the Mobius strip configuration null-bordant. Um, I agree, but I don't know what that object is.
Okay,
Um, yeah, so yeah, I don't know what the M theory or Hajava-Witten version of the seven brain is. Yeah, I'm not sure how to think about it.
okay. Well, thank you.
Yeah.
Thank you very much.
No, thank you for the question. Yeah, there's many mysteries, I should say. There's various things I don't understand, but yeah, that's a good question. Thank you. Any other questions? Okay.
Yeah, sorry, Justin,
Oh yes.
can I ask a
Yeah,
question?
please.
So,
Oh, please. Yeah, yeah, yeah.
do you know how these sort of brains behave under T duality? So if you go between these two heterotic, the standard
Um,
heterotic theories?
Sort of. Well, I'll give you some list of potential dualities at the end of this talk, somewhat motivated by TMF. Um,
Okay,
there are also other dualities which are that appear in one paper by Kazuya, which relates the six brain to the NS5 brain. But I'll give you some other dualities at the end of this talk. Yeah.
okay, great.
At least they're T dualities in the sense of weak dualities.
Yeah,
They're not just circle compactifications, of course, for many of them. One
okay,
of them will be. Anyways, I'll tell you in a second.
thank you.
Yeah, thank you. Okay, any other questions? Okay, good. So then let's move on. So now I'm going to make some more math-oriented comments. I'm obviously not a mathematician, so it'll still be physicsy, but slightly more math-oriented. So the first thing that I'm going to do here is I'm going to define this sequence of groups SQFTN. What is this? It's basically the set of 0, 1 SQFTs, which have some gravitational anomaly n, okay, in units where a chiral fermion would contribute 1 to this thing. Okay, so if your SQFT is actually a CFT, then in that case, you can just take this to be 2 times the chiral central charge. But more generally, even if it's not a CFT, you can still define this gravitational anomaly, right? Okay, so SQFT-N is basically just this set here, modulo some sort of equivalence relation, where sort of morally speaking, the equivalence relation is identification by continuous deformations. Okay, but where by continuous deformation, I mean something extremely broad, like not just flowing down an RG flow, but also flowing up an RG flow to some parent theory and then back down to some other daughter theory. So I would call all of those things in the same equivalence class. And to say this slightly more concretely, so this is really just some sort of Bordism. So, uh, so what I can do is the following. Let's say that my theory, yn plus 1, my SQFT, has a boundary, okay, um, if it has a non-compact direction, okay, which I mean in the sense of the energy spectrum, okay, so there's some direction in which it becomes continuous, okay, where basically the theory ends up looking like R, okay, so just a free 0, 1 R sigma model, right? Uh, times xn. You see, you get a shift of 1 here just because I've pulled out one chiral fermion, which is part of this R piece. Right? And so you get a shift in the gravitational anomaly by 1. So, okay, so I say that y has a boundary if there's some limit, some direction in which it looks like this. Okay, and then I would say that this theory here is like a boundary of y and plus 1. And then I introduce some equivalence relation, which says that these two things are equivalent if and only if there's some interpolating theory, okay, some theory such that you have the same, such that the boundary is like the union of the two things, or at least includes the union of two things. So it's like some version of Bordism. Okay. Now there's a conjecture that whatever this thing is, when you properly define it, it's actually equal to some math thing called TMFN. So what is TMF? It's some spectrum. It's the next thing in the chromatic homotopy sequence after K theory. And there's a lot of fancy math that goes way over my head in describing this, but for our purposes, it's basically just some sequence of groups. Okay, for every n, you'll have some group, and remarkably, mathematicians have computed these groups. And so, for example, in the range where n is minus 31 to minus 22, which is what I'll use in this talk, it turns out that these groups just look like this. Okay. Now, what are the invariants that label a TMF class? Okay, so what labels if you're in this versus in the like trivial element of this versus the non-trivial element? Okay. Well, obviously, one invariant of these classes is the following. So given any SQFT, we know that we can compute its elliptic genus. Okay. Sometimes you'll have an ordinary elliptic genus, sometimes you'll have a mod 2 elliptic genus, depending on what the gravitational anomaly is. But in any case, you have this elliptic genus, which is basically some morphism from SQFTs to, well, right, it spits out some modular form. So the ring of Laurent polynomials in Q with coefficients in KO. Basically, so KO is either Z or Z2. And when it's Z, you have an ordinary elliptic genus. When it's Z2, you have a mod 2 elliptic genus. I can explain that more later if you're interested. So ask me. But anyways, so given an SQFT, one invariant is, of course, the elliptic genus, either ordinary or mod 2. And so that gives one thing that can specify which TMF class you're in. But is the elliptic genus actually a complete invariant? Does it completely specify which class you're in? And it turns out that the answer is no. In particular, these guys in blue here, it turns out that these things live in the kernel of the elliptic genus map. So they have 0 ordinary and mod 2 elliptic genus. Okay, so there's no way to use the elliptic genus to tell if you're in the trivial or non-trivial part of the Z2. So this, in some sense, is really the most interesting part of TMF. It's these guys here that can't just be distinguished using familiar invariants like the elliptic genus. Okay. These are the really interesting guys. Okay, now why am I talking about this? Let's make connection with our branes. So remember that for our branes, right, we had this as the angular theory of the branes. And there was some flux that glued this G1 to this sphere in some appropriate way. Okay. And remember that I showed that there was some RG flow, or maybe you had to add in some, you had some tachyons or something that allowed you to express it as some current algebra theory HK. So because there's some continuous deformation connecting these two things, they're in the same TMF class. Okay. And which TMF class are they in? Okay. Well, first of all, let's just compute the gravitational anomaly here, which in this case is just 2 times the chiral central charge. Okay. So for the we can compute it on either side, but let's just compute it here. So the current algebra piece has chiral central charge, which is, well, it has central charges, which are these 16, 0. For the sphere part, right, you just, so you have contributions from the bosons on both sides, and then you have a contribution from fermions on the right. The right is the supersymmetric side. Okay, so this is your central charges. And so the gravitational anomaly that you would have for this case, oops, for this case is minus p minus 24. Okay, so for the 7 brane, this theory, or equivalently, this theory would be in TMF minus 31, and so on and so forth. Okay, minus 30, minus 28, minus 24. Now, going back to this previous, I gave sort of a list of some TMF groups. So the highlighted ones are where our branes live, where the angular theory is describing our branes lives. Okay, so this is where the 7 brane angular theory would live. This is for the 6 brane, the 4 brane, the 0 brane here. Now, for the 0 brane, you can basically just compute the elliptic genus of the theory, and you'll immediately find that it's non-trivial. Okay, so the angular theory for the 0 brane just lives in one of these two things. It's not that interesting. But what's really interesting is that for the other 3 cases, you can actually check that the elliptic genus for the angular theories is 0, both the ordinary and mod 2 elliptic genus. Okay, and so those theories live in these blue parts, these really interesting parts of TMF. And in particular, you can actually show that they're the generators. So they're the non-trivial elements of these blue Z2s here. Okay. So the angular theories for the new branes are captured by these non-trivial TMF classes here. And so, sort of morally speaking, what it seems like is like TMF is giving some worldsheet version of brane charges in the heterotic string theory. In the space-time point of view, right, you are measuring some sort of non-trivial something, maybe a characteristic class, say, on a sphere at infinity, and the TMF, or sorry, the worldsheet version of this is like saying that you have a worldsheet angular theory and you check if it's in the non-trivial TMF class or not. So that's sort of morally speaking, one way to think about this, but there are important caveats. So this is not really correct. And this thing can fail to be correct in multiple directions. First of all, TMF can sometimes be too small. So, for example, if you look at the angular part of an NS5 brane, it's actually trivial in TMF, right? Because it's trivial in Bordism. So I can always, there's a null Bordism from S3 with unit H flux by just inserting some instanton in the middle, right? Um, So, so TMF doesn't, for example, capture the NS5 brane. Okay. Of course, there might be some refinements that do capture the NS5 brane. For example, we could consider equivariant TMF, where you require that G is, so you're considering interpolating theories that have a G global symmetry. Okay. The previous Bordism involving the instanton would break the G symmetry, so that uh, so this class could be trivial in normal TMF, but maybe not in equivariant TMF. But okay, anyways, there could be various refinements, but you see that as currently stated, this TMF can be too small. It can also be too big. Okay. Basically because, so we usually measure charges by considering some sphere at infinity that surrounds the brane. Of course, if you have not just a brane, but some sort of singularity, something like an orbifold or something like that, it might change what you have at infinity. Okay. You might not have a sphere, in other words. You might have a quotient of a sphere if you have an orbifold or something like that. But for a normal brane, we usually just expect to have a sphere at infinity. But of course, for a generic TMF class, there might not be any interpretation as like having a sphere in it, right? So above for our TMF classes, we always had some description in terms of where we had some sphere here and the current algebra fibered over the sphere. But in general, we might not have that. Okay, so maybe TMF classes are too big. Okay, that being said, you still might be able to use this sort of TMF language to do various useful things. For example, um, understanding discrete theta angles. So this is something that we do in the paper that I'm not going to describe here. Another thing is that you could try to motivate dualities. Okay, and so for example, one thing that you can show is that if you take this class where the angular theory of the seven brane lives, and you multiply it by the class of a circle with non-bounding spin structure, then you get the class where the angular theory of the six brane lives. And this then motivates the following duality. It motivates that if you put a seven brane on the S1 with non-bounding spin structure, so periodic spin structure, then that should be equivalent to, in other words, T dual basically, to the six brane. Now, of course, the precise duality might require some appropriate Wilson lines on the circle, and I don't think that TMF really tells us about that. I'm not sure. Maybe if I thought more about this, yeah, I'm not sure. But if you put appropriate Wilson lines, my guess would be that this is T-dual to this. Okay. And in a similar way, you could get a bunch of other identities here that I guess I'll just flash, but I won't explain. So, okay, let me just summarize um, and then we can have questions. So the upshot is that we found a 0 and a 6 brane in the SO32 heterotic string and a 4 and a 7 brane in the E8 cross E8 heterotic string. I showed that the near horizon limits of these branes were described by stable lower dimensional vacua of the non-SUSY heterotic strings. And by the holographic dictionary, you actually expect these lower dimensional vacua to be sort of equivalent to the world volume theories of the branes themselves. Okay. So sort of my takeaway from this is, why do these 10D non-SUSY heterotic strings exist? My claim is that they exist because they are the worldsheet theories. They're the world volume theories of some new non-SUSY branes. Okay, they're just the world volume theories written in a really funny way, where first of all, you try to think of it as written in 10D Minkowski space instead of lower dimensional linear dilaton background. And then you also didn't use the holographic dictionary. But if you had done those two things, you would see that they're actually completely equivalent. So that's one takeaway. And there are also intriguing connections to TMF, which remain to be fully understood. We discuss some of them in the paper, and some of them we do not. And of course, there are other non-SUSY branes that other groups are uncovering. And so I think this is a very interesting topic to be studying. Okay, that's it.